Hello everyone. We will continue with the lecture on convex sets. So we were here last time, if you can recall, we were talking about ellipsorts. So in the 2D case, ellipsort will look like this. So we will have a center here, okay, XC, and then we have an ellipse. So ellipse we know, okay, and then if you include everything inside, okay, then it will be an ellipsoid in R2. So this is an ellipsoid in R2. And we also learned from last time is that we can write this compactly in this form. Okay, so an ellipsoid with center at XC can be written in this form. Okay, so we have seen this last time with some examples, and it's essential that P is symmetric and positive definite. That's also we saw. If it is indefinite, then it may become a hyperboloid. Okay, so another thing we noticed is how far so the eigenvalues of P play a role in knowing which is the major axis and which is the minor axis. Okay, so in this case it's R2. So P will be a 2 by 2 matrix. So this will be R2 by 2. Okay, and it will have two eigenvalues. So it will have two eigenvalues, let us say lambda max and lambda min. So lambda max will point in this direction. I mean, not the eigenvalue, but let us say the eigenvector V max. And V min will point in this direction. Okay, so this is something we saw in the last class. So the eigenvalues play a role in how far your ellipse will stretch in along one axis and so on. So this is what I described. So it's proportional. The semi-axis length of semi-axis is proportional to the eigenvalues lambda I. So these are eigenvalues of P. If you indeed are looking for a ball instead of an ellipsoid, then you can put both the eigenvalues equal. That would mean that the stretching in either direction is the same, and that is how you get a ball. Okay, and what is the radius of that? That will be determined by this R square. And then we saw that another way to write an ellipsoid is like this, where we have XC plus AU. Okay, so XC, as you can see, was the center. So you can say as if you are starting from X and you are trying to see how far you can go. So starting, let us say you start from XC and then let us say you make a unit ball. Okay, so let us say this is of radius 1. Okay, so this ball we can determine. Let us say this is the set of all U. Okay, so let us say small u such that norm of u is less than equal to 1. Okay, so you have made a unit ball here. This is the set u, and you are at XC, and now you want to see what is the action of A on those u, and then how far I can go from the center. Okay, so you can take any vector from here. Let us say V is in U. Okay, so this means that norm of V is less than equal to 1. Okay, so this means and then what I'm looking for is XC plus A times V. Okay, now it depends on how V is aligned. Okay, so if it so happens that V happens to be along the largest eigenvector of A, so if V along, let us say V max the largest eigenvector of A, then you will stretch the most. Okay, so the output this will be stretched the most. For example, in this case, if the eigenvector of A is this way, then the unit vector that you have here, if it is aligned on this way, so this will be stretched the most. Okay, and how far it will be stretched? It will be stretched by lambda max. Okay, so let us say in this special case, we will have xc plus lambda max, okay, of V. Okay. Okay, so you took some vector V from U. Okay, so let us say this is the vector V, and it happens to be along the eigenvector of A, which is V max. Then the amount you will be stretched is lambda max V. Okay, same thing, same arguments you can make from here. Okay, now there will be conditions when
Hello, sir.
Hello.
Yeah, sir. So you are saying that V is the corresponding eigenvector of lambda max.
Yeah, exactly. V is the corresponding eigenvector, right? So I want to see what are the other scenario, right? So there are cases where you get aligned along the eigenvector, right? But there are also cases where you can point in this direction, right? So let me clear this. Okay, so let us
Hello,
see.
sir.
Hello, yes.
Yeah, I had a doubt. So in the ellipsoid equation, P
Yeah.
is symmetric positive definite. So
Yes.
according to the definition of symmetric positive definite, X transpose Px is greater than 0, right?
Yeah.
Because that is the quadratic form, and if P is a symmetric positive definite, its minima will be in 0. But here in the equation, it is written less than equals 1. So
No, but there is an offset here also, right? So this is this offset
acha, this X.
will go to the right hand side, right?
Okay, yes.
Okay. So you can rewrite this. So this
Okay.
will be like X transpose PX, and then this is like minus XC transpose PX, and then there are terms like plus XC transpose PXC. Okay, so there are these known terms that will go on the right hand side, and that may make it the right hand side different, right? Okay, in other words, like in other words, what you're saying is like x minus xc. Okay, it may still be like greater than equal to 0, but what I am asking for is that it has to be less than equal to 1. So I mean, there is nothing harming this to be still greater than equal to 0, because there is still this is way beyond 0, right? So this 0 is here, 1 is here. So it can still lie within this. Okay. So even if these guys are not 0, x minus xc is not equal to 0, then since P is positive definite, then this would imply x minus xc transpose P x minus xc is greater than equal to 0. Okay. But what we are additionally asking is that it's less than equal to 1. Okay, so I mean, it doesn't violate anything yet. Okay, so that's fine. Okay, yeah, yeah. So okay,
Yes, sir.
so yeah. Okay, so let me continue then. So I talked about vectors.
Vishnu,
If
let
I
me
if I had center, then if I go along this axis, then I will get stretched, and if I go along the minimum eigenvector direction, then I get less stretched. I mean, it may still be stretched. It depends how are lambda max and lambda mean. Depending on that, relatively I will be less stretched or more stretched or contracted. It depends, right? Now you may ask, like, what happens with these guys, right? So these guys, let us say we can again draw the unit, because we are restricting these guys on the unit. So again, I look something in this direction. Okay, so now it is neither aligned along this or this, right? But the thing is that for any other vector, okay, important thing is, like, okay, so we are talking about symmetric and positive definite, right? So symmetric positive definite matrix has n linearly independent eigenvectors. You recall this, okay? So if P is symmetric, then it implies P has n linearly independent eigenvectors. Okay. Look for this course, like, it's not really necessary, but if you want to really understand this course, then I'm giving you all the things. Like, you will be doing a lot of optimization and not like gradient method and so on. So it's fine, but but you see how things come into picture. So what do I mean here, right? So P is a symmetric. Okay, just symmetric is enough to guarantee you n linearly independent eigenvector. Well, if n linearly independent eigenvector are there, then it means that they form the basis. So we have a eigenbasis. We have a basis for the space. Okay, yeah, Rn in this case, right? If there is a basis, then this means that any arbitrary vector that I have here, I can write this using those eigenvector. So let us say this is the v eigen v1, let us say, and this is the second eigenvector v2. So any vector here, let us say this is the vector z. Okay, so this z, now since v1 and v2 form the basis, okay, and these are the eigenvectors of P, which does give us a basis because it's symmetric. So z now can be written in terms of these, so alpha v1 plus beta v2. Okay, that's what basis means. That using those basis vectors, I can express any vector. Okay. So now the question is where these guys stretch, right? So where these guys will stretch now will depend on the relative components of alpha and beta. So for instance, if I am closer to the lambda max, then I will stretch a lot more in this direction because that component is bigger, right? So that component will be bigger if I am closer to v1, because let us draw the this axis here, right? Let us say my vector is closer to this eigenbasis, right? And this is another eigenbasis. That means that I have more of this component. Okay, so you see this. If I'm closer to this, then I have more of this and less is the height. Okay, so this means that alpha is way greater. So this means like way greater than beta. Okay, so this means that this component will be amplified more. So this will go more. It will make more of the v1 component than v2 component. Okay, this is like the geometrical meaning, but you can already guess. And similarly, since this component was less, which is beta is less, so its height will relative to the x component, its height is going to be still smaller. Okay, so now you get the idea of what will happen to all these vectors, right? And this is why you end up getting this oval shape. Okay, so the vectors here are still going far, right? Like it's not like the vector here went the farthest and then it suddenly like dropped. It was not the case. It's going smoothly like this. Okay, so the vectors are less and less stressed, less and less stressed, less and less stressed, less and less stressed. And if you take them in this direction, you are the least stressed. Okay, although they are all the unit vectors, all the vectors that we are testing are on the unit vector. but relatively those are stressed more which are along the lambda, which has more component along the largest eigenvector. Okay, so this the reason why I spent a little bit time here is actually it will show up in steepest descent. Okay, steepest descent is a more general variant of optimization solver, and steepest descent, the idea of steepest descent is like you will be standing somewhere on a mountain hill, like you can think of functions like some mountain valley. You are there, and then at each point in your current iterate xi, you will be looking for how to descend. Your objective is to go to minima. So each time you will be trying to estimate the landscape. Okay, trying to estimate the landscape and what is the preference that you want to have. Okay, which direction you want to, because when you are looking, you have a local view of this. Okay, imagine these mountain valleys are very big. So so a choice of norm will tell you the local information about the valley that you are in. Okay, and based on that you will start descending. For instance, if you take a 2 norm gives you a very unique preference in every direction. Okay, so if you are going in this, then you don't have any preference at all. Okay, but actually maybe I'm shooting the gun here. Actually this could be written as a p norm. Okay, so what this is actually p norm, the matrix P. Okay, I will define these things later. Okay, so if I am changing the norm, I am changing the landscape, and if I'm changing the landscape, and P could be like, maybe again I'm like shooting the gun here, like P could be like your local curvature, like Hessian of your function. Okay, the Hessian gives you the quadratic approximation local. Okay, so if I employ something like this, then locally it is giving me quadratic approximation. Okay, so then I have this view, and if I have this view, then I will have certain preference to descend in certain directions so that I descend faster. Okay, this may not make sense right now, I know, but just keep these things in mind. Okay, like there is a lot to do with the norms, and norms are nothing but local area estimates and the preference that it is giving me. Okay, forget it. Okay, just forget it for the moment. This will come after 2-3 lectures. Okay. Okay, so so there are intentions behind what we are doing it right now. Okay, and eigenvalue, eigenvector, all this plays a role. Okay, some of you might already see what I'm trying to say. Okay, that's why I told this. Okay, so but anyway, don't worry if you don't understand it now. Okay, so this is the this is a nice connection between eigenvector, stretching, norms, and now in the hindsight, somehow I introduced a P, tried to give you intuition behind matrix norms. Okay. Anyway, we will see this. Okay, let us stick to the convex set now. Okay, so what I want to describe the next object, the next geometrical object is something called norm cone. Okay, norm cone. Now, the norm cone is defined to be like this. Okay, if it is not mentioned anywhere, just take it as a 2 norm. Okay. Okay, so it's like a 2 norm. So these are the set of elements x comma t such that norm of x is less than equal to t. Okay, and obviously since so this as a pair, this is in n+1. So this suggests that x is in n. Okay, and t is in r. Okay, this t is in r. Okay, so so we are taking a Cartesian product. And then we get elements like this. So this is why it is in n+1. Okay, this is in n, this is in R1. Okay, so we understand this set, and the most important part is this, right? Like we are relating n components with the last n-1 component, and that should be less. Like, so can you already visualize this this object, right? Can you visualize this this object, right? So this is how it will look like, and that is why it's called a cone. Okay, norm cone. So you can play with this, right? So let us say for us the easiest thing is R2, right? So n is 2. So then Rn plus 1 is 3, right? So we have a cone in let us say 3 dimension, right? N plus 1. And let us play with some entry. So let us say my vector is x1, x2. So I write this in expanded form. The whole thing will be x. And let us say I choose some t. Okay. Then what this is, it has to satisfy this. So this means that the norm of x1, x2, since I am considering two norm, so this is like x1 square plus x2 square root is less than equal to t. Okay. So this is like x1 square plus x2 square is less than equal to t square. Okay. So yeah, so from here what we understand is like set of all x1, x2 which are in the centered at origin, right? So circle with center at origin and radius. So circle with center 0, 0 and radius equals to t, right? So for a fixed t, and it's not just a circle, basically it's a disk. I mean, equality is a circle, but if you do less than equal to, then inside part will be taken, right? So disk, okay, with center. So now you can see, right? So if I fix a t arbitrary somewhere here, okay, so this is the t is the height I'm taking, and this is the x1, and this is x2, and this is x1. So these are the I mean the corresponding x1, x2 will be on this xy plane, right? So x1, x2 plane. But since you are appending it with t, so you are making up the height also. So these points then move up. Okay. So you are asking for set of all x1, x2 such that it's equal to t. So those x1, x2s are here. Okay. The pairs of x1, x2 that satisfy this equals to t square are this, and not just equal but less than equal. So this will be this is a center at origin. So this is somewhere the origin is here, let us say. So the disk is this. So these are for the moment these are x1 and x2 that lies on here x1, x2 plane. But if I append t also, then I give it a height, right? So if I append a t also here, then I give a height, right? So if I append a t here, then this guy will move up in 3D. So these points are now this. So that's what these points mean, right? X comma t. So basically these are these disks at varying height, and if you do it for continuous t, then this will become a cone. And interior part is also included because this is less than equal to. Okay, so all interior part is needed and so on. So it's a cone. Okay, now you agree this is a geometrical object, but sometimes the maths, the way it is written is sometimes it requires some thinking. But this is a cone, and you can prove that. So you can take this as an exercise. I will ask my TS to now start preparing some assignments. So here you can take this as an exercise that this is convex. I mean you can look here and you can immediately say it's convex because I take any arbitrary line points and then I join a line and whole line is guaranteed to be inside the cone. So that's very intuitive, but what I want is a concrete proof of this, let us say. So you assume that xt is in here, and then you assume some another point. Okay, so let us say another point yt is in here. Okay, and then you
Sir, I have a doubt here. In the last class, you told that if the line joining 2 points should also belong to the set, but
yeah.
in this cone, it won't. It will be only in the border, right? Not in the center, right?
But a disk is included. The inside points are included, right? Because it's less than equal to. It's not just points that
Yes.
satisfy the circle, but also the ones that are inside, right? This less than equal to is here.
Yes, sir. Yes, I get it.
Yeah, then so inside points are there. So whole line will be there inside, right? Okay.
Hello.
Okay, good. Okay, good question. So, yeah, yes.
Another doubt, sir. How is this related to the norm set we saw earlier, where we had those diamonds and circles in 2Ds?
Yeah, so norm sets, like we discussed norms, various types of norms, right? So we discussed like two norms. We discussed infinity norm that goes like this and so on, and one norm that goes like diamond and so on. So here it's like it's first of all like those are also like some geometrical objects, and here in the case of norms, the set of points that satisfies two norms. So the way we wrote it there was just x. Here we are bringing in t also, right? So that's why it becomes a cone. Because if you see the norm balls, right? So we call those norm balls. Although they are not really like ball, but if you see in the abstract maths, even these things are called a ball, okay? Because it's just a ball with a different norm, okay? So we don't care. I mean, ball should not look like a ball itself, right? So in the norm ball, if you recall, let us say I'm looking for ball, two norm ball, okay? So that will be norm of x, okay? And let us say I'm looking for the unit norm ball. So there's like a radius is like 1, so this is equal to 1, okay? So set of all x as that. So the difference here is, okay, or I can also make this equal, right? So here in the ball, what I'm asking for is set of all x as that 2 norm of x is less than or equal to 1. So that's like this ball, and then everything inside the circle, okay? So that's like a unit circle, or like a disk here. Also inside parts are there. Here the difference is like x is separated out from t, okay? And now we are relating the first n components with the n plus 1th components, and this is the n plus 1th components. So that's why the shape changes. Okay, there was no such constraint like this here in this case. Okay, it was just the thing that is very different is like the first n components get related to the n plus 1th component. Nothing like this happens here in the norm balls case. Okay, and that is why you get this unique shape, and the explanation is like just like what I said, right? Why it is coming is like I just proved it, right? Because as the height t is increasing, your disks are getting bigger and bigger. So that's the only change. Okay, your disks are getting bigger and bigger, and so on. So that's how it will behave, like it will look like a cone. Okay.
So we are reading the value of t here.
Yeah, so it is like for all values of t, right? Okay. So we are like we are changing the values of t.
Okay, also. So got it.
Yeah, we are also changing the values of t. Yes. Okay, that's also a good question. Okay, so we are considering all possible x and t. Okay, both are changing. Okay, so that way, like you take all possibilities and it will fill up as a cone. Okay. Okay, so that's another geometric object. So in optimization theory, there is sometimes you may be working on a cone-like domain. Okay, so there are like separate areas of like conic programming or something like that. Okay, so where you know for sure that my data is like lying with certain restrictions or something that is creating a cone-like thing. Okay, it may be like it. You may imagine this like some constraint is there on your input data, right? So you can imagine like some of the first things in your data must be bounded by the last feature in your data. Okay, something like that. Okay, I'm not saying, but these things we will see some applications where these things will show up concretely. But even the data may have features may have some relations between them, and that may create some additional geometry that you may have to enforce, because these are enforced, like these are constraints that you are given by someone, and that creates a certain geometry And on those geometries, then you have to deal with the functions, minimizations, maximizations, and so on. So that's why geometry plays a role. Okay, and depending on geometry, your class of algorithm that you want to do will change. In fact, drastically changes. Okay, because theory changes a bit. Okay, and just naive application of the algorithms may not work. Okay, we will see this. That's the goal of this course. Yeah, so sometimes it's called quadratic cone, Lorentz cone, ice cream cone. Okay, so depending on papers, you can see a variety of names given to this. Okay. Okay. Now another geometric object we are interested in is something called polyhedron. Okay, so polyhedron can contain actually many things as a special case. Okay, so for instance, polyhedron as a special case can represent a half space. Okay, can represent a hyperplane and so on. Okay, so by polyhedron, we should not always think that it's always something closed. Okay, okay, so that's the doubt that I would like to clarify from beginning after teaching this course for last 2 years. Okay, so polyhedron should not be according to the definition that we are giving here. Okay, actually the distinction we will make is like polytop will be like closed, and okay, polyhedron not necessarily. Okay, and that follows from the definition itself that it is not necessarily closed. Okay, because let us say I have m just 0, right? So because or m is 1. Okay, so let us say just m is 1 and d and p is 1, let us say. So then it's the intersection of a hyperplane with a half space. So that will be like something extended, just like this, right? Because I may have a half plane here, which is given by this. So let us say my half plane is ax less than equal to b, and my hyperplane was ax equals to b. So this is the hyperplane, and the half space is this. If I take an intersection of this, because both has to be satisfied, right? Since both has to be satisfied, then it means intersecting those things. Then I will get a line, and it's not necessarily a closed thing, right? So you will think, okay, how come line is a polyhedron? So according to the definition here, it will be a polyhedron. Okay, because we have to satisfy the intersection. Okay, so okay, so let me so let us see some special cases of this. So what does this say? This is the intersection of finite number, because m should be finite and p should be finite. So it's intersection of half spaces. We have learned that this is a half space and this is a hyperplane. Okay, so it's just an intersection of these. So for instance, it may look like this. So closed cases can be considered, but may not be always the case, right? So so this is, so what do you think in this case? So how could you have obtained this by using half spaces and hyperplanes? So how many half spaces you have to intersect to get this shape? Okay, by this shape I mean there's something inside also. Okay, so how many half spaces need to be intersected?
5 half spaces.
5. Okay, so
and no hyperplanes.
Yeah, yeah. So it's like you don't need any hyperplane here, because like boundary is like anyway there. Okay, so in less than equal to is there, right? So if we indeed need the boundary, okay. So in this case, the half spaces would be like, let us say A1 transpose X. So that's the normal, right? So less than equal to B1. A2 transpose X is less than equal to B2, and so on. So there are 5 of them. A5 transpose X is less than equal to B5. Okay, so this is the intersection of these, right? So these guys, so this must be one hyperplane, and this must be another hyperplane, and this must be another hyperplane, and so on. So 5 of these I take and then intersect, and that's what I get. Yeah, so the question is, which of the following are polyhedron? Are hyperplanes polyhedron? Yes, so that's the example that I gave before. Okay, so and then lines are also okay because it could be like intersection of just yeah, just the hyperplanes, right? And then half spaces. So half spaces, again, we already saw. I just have one equation here, and that will be the half space. Okay, so it could be just this. Okay, it is not necessary that I have to have this. Okay, or it could be just this, or it could be a mix of both. Okay, so by combining, I can get a lot of stuff. Okay, so by intersecting two hyperplanes, I can get a line. Okay, so let us say one of the plane is this, and another of the plane is this. Okay, so assuming that they're intersecting, so they will intersect somewhere on a line, right? So that line I can get by intersecting, let us say, two hyperplanes. Okay, and half spaces I get, right?
Sir,
Yeah.
can a single half space be a polyhedron? It can't.
Yeah, it is also. You just take m equals to 1. Okay, so you just take A transpose X is less than equal to B. This is the single half space. You don't take any of this. Okay, you are allowed to do. Okay, you are allowed to take any just one equation, any of this, any combination of this. Okay, or you just combine also and intersect. So it's possible. Yes.
Closed spaces.
It could be closed. It may not be closed. Okay, it doesn't matter. So it doesn't matter. So that's what I said in the beginning. Polyhedron, the way we define is like is not necessarily closed. But if it is closed, if it is like bounded, then we give it a name which is called polytope. Okay, so if indeed we want a closed, which is here, then we will give it a name like polytope. Okay, so in case you see books and so on where they define polyhedron as closed thing, then this is the disclaimer that I want to make here, that for us the term polytope will be reserved for bounded polyhedron, and otherwise polyhedron will include hyperplane, lines, half spaces, unbounded. Yeah, it could be unbounded, but they are always like this, like these things can never be a polyhedron, right? Because polyhedrons don't have curvatures like this. Okay, these are made up of this, so they will always be like, if they intersect, there will be sharp corner and so on, right? You cannot generate something like this. You can generate this provided you are allowed to choose m to be infinity, right? Then you may be able to. So by doing an infinite number of this, you may in a asymptotic case, you may make it a circle, but that is taken away from by putting this restriction that you must have a finite. So you cannot generate this this curve-like things, because for curve-like things you need to intersect infinitely many half spaces to get this curve, but that won't be possible, right? So if whenever someone gives you something like this, very curvy thing, then you immediately say it's not a polyhedron. Okay, polyhedron can be compactly represented as also like this. Okay, so matrices using matrices. Okay, so if you go back and if you see here, this is a sequence of inequalities to satisfy, and if I write down all this, then I can absorb AJs into matrix rows. Okay, so A1, okay, A1 transpose, okay, and then A2 transpose another row and so on, and let us say AM transpose. So I can write all this in one shot, and they all multiply with X, and then B's are like B1, B2, and BM. So this is the matrix A. Okay, so all these M inequalities can be written in compactly as A times X is equal to B vector. Okay, similarly C, okay, I'm missing this here. Okay, this should be J here. Okay, C is not a constant here. C should vary because we are talking about a multiple number of hyperplanes. Okay, if you fix C, that will just one. That doesn't make sense. So that's what you're saying here. Yeah.
So can a circle be polyhedron?
Which one? Can?
Circle or a norm?
No, that's what I said, right? Just now I described, right? Polyhedron by definition can't be a circle. Okay, so it can't be a circle. Because for circle, you cannot obtain a circle by intersecting finite number of hyperplanes and hyperplanes. Okay, half spaces and hyperplanes. You cannot do that. As I said just now, to get a curvature like this, you need infinite number of intersections to get a curvature like this. Okay, that's not possible.
Okay.
Circle it can be treated as a polytope, but with a infinite sides, right? But that infiniteness is not allowed here for us. Okay, in the definition. Okay.
Okay. So can we have zero hyperplanes or half spaces?
Can we have?
Zero hyperplane.
Yes, I mean in this case here we can disregard this. Let us say half spaces, hyperplane, and we can take only half space. So that you are allowed. But if you take both 0, then it's an empty set, right? So then it doesn't make sense. You take couple of these, like you take one of these, two of these, mix hyperplane half spaces. So to answer your question, you may make half hyperplane 0, or you may make half spaces 0, or if you take both 0, then this is no geometry, like nothing is obtained. So you are allowed to make one of these 0. Okay, so we can compactly write polyhedron as this form. Okay, that's what happens when you go for higher dimensional problems. Things get transformed into matrices and vector, and that is why linear algebra becomes important in regardless of which field you work in. Okay. Okay, so that's what I explained. This is the A and this is the C matrix. So one example of a polyhedron is this. Okay. Previously, I showed you some geometric illustration, just a geometrical figure, but you can take this as one example. So what is this? This is like a non-negative orthant. So that you already know. Non-negative orthant is this part of the coordinate R2 plane, right? So this is very simply just it is the intersection of half spaces. Which two half spaces? Like x1 greater than equal to 0, right? x2 greater than equal to 0, and so on, and xn greater than equal to 0. Okay, so this is a half space, right? What is x1 greater than equal to 0? X1 greater than equal to 0 is this thing. Okay, so this is our x1, and this is x2, and x2 greater than equal to 0 is this thing. Okay, so since both have to be satisfied simultaneously, okay, so hence if you take intersection, then you will end up getting this as an intersection. Okay, you extend this to n-dimensional case, and then so non-negative orthant is nothing but a polyhedron, and it can be written as intersection of half spaces. Okay. There are objects so-called simplexes, and simplexes are another family of polyhedra. Okay, so polyhedra we saw is like it's like a bounded form of polyhedron. So simplexes are going to be bounded. Okay, now for simplexes, people came up with some definition of dimension. Okay, so far from linear algebra, what we know is like dimension is defined for a vector space, but we can give dimensions also to geometrical objects such as simplexes. Okay, so let us see how we define dimension for that. Like for instance, someone tells you like a sphere in 3D, right? So then you say that it's like a 3D object, right? It's like a 3-dimensional, but the 3-dimension that we are talking about is like a affine dimension, right? So that's but it's not a vector space. Like this set is not a vector space, so it's not a vector space dimension we are talking about. So okay, so let us define the affine dimension here. A set of k plus 1 vectors are called affinely independent if there is a vector v0 in the set, okay, such that v1 minus the same vector, okay, so we know v1 minus v0, v2 minus v0, dot vk minus v0, they become linearly independent. Okay, and this is linearly independent in the sense of vector space that we talked about. Okay, so the usual linearly independent. Okay, so then we call it to be affinely independent. Okay, then we call it to be affinely independent. So the simplex determined by V0 to Vk is defined as follows. So you take a convex hull of this. Okay, so the convex hull, what was that? We saw it's like all possible convex combination of these guys. Okay, you take all possible convex. What was convex combination? It was theta 0, V0, and so on. It's like a linear combination, but the restriction was that theta is greater than equal to 0. So theta is the vector here that denotes theta 0, theta 1, dot dot theta k. Okay. So you remember the convex combination was this. Each of the theta I must be greater than equal to 0. So that's satisfied here, and the sum of the theta must be 1. Okay. So you take all possible convex combination, and then what you get is a simplex. Okay, what you get is a simplex, and so the affine dimension of this simplex is k. Okay, so you start with k affinely independent vectors, and then you take a convex. You convexify. Okay, so you make a convex hull of that. That is, you take all possible convex combinations of this vector, and what you end up with is a simplex. Okay, and that simplex dimension will be k because you generated it via k affinely independent vectors. Okay, so that's the difference between the usual vectors and then the simplex. So the usual simplex will look like this. Okay, so this is, so remember, okay, so simplex is a polyhedra. Okay, so simplex is a polyhedra, and polyhedra is a special case of polyhedron. Okay, so someone asks you, then simplex is also a special case of polyhedron, but it's just that it comes up more frequently. So that's why people try to study this as a separate object, and also define dimensions and so on. Okay, so simplex is a polyhedra. Polyhedra is nothing but a polyhedron. The difference is that simplex now also comes with a kind of basis you can think of. Okay, so it's kind of basis, like a fine basis you can think of, right? Because we are now talking about linearly independent k linear independent vector that generates this geometric object. Okay, so you can think of simplex of certain dimension is coming up with some basis vectors that is used to generate via convex combination, that is used to generate all the points in here. So in this figure, if you think about, then this could be your V0, this could be your V1. There is nothing specific about V0 here. Okay, you pick any of these as V0. Okay, V0, V1, V2. Okay, so to generate a simplex, you have to make sure that V1 minus V0 and V2 minus V0. Okay, let us say. So I fix one of these, and then this should be linearly independent. If this is linearly independent, then I will go ahead and form a convex combination, and that will always give me a simplex. Okay, and the dimension of that simplex will be k. Okay, not k plus 1. Okay, you see here there are k plus 1 vectors, but the dimension of the simplex we will call it to be k. Okay, so the affine dimension of this simplex will be k.
So if we take k plus 1 vector spaces vector k plus 1 vector space, even they will be affinely independent. So why are we again considering this V1 minus V0 and so on should be linearly independent? Is there any reason for this?
Yeah, because look, yeah, I mean, first of all, we want to give a dimension to this. So, so the dimension, the way we will give dimension is via the so-called affine dimension, because this is not really a linear space, right? Vector spaces are linear in the sense like 0 vector is also there, but these guys are not really may not necessarily have 0 because origin may be somewhere here. So for these cases, we need to define affine independence separately. Okay, so affine independence, the concept of affine independence comes into picture. But so that's why we define it in a non-traditional, or let's say in a separate way, and hence the concept of these things come. So because even for a vector space, if you see, vector spaces are unbounded spaces. Okay, it's like you keep going because you can keep adding, multiplying, and so on, and you start filling up whole of thing. But these are like bounded, right? So they have certain constraints here, and that is what creates these bounds for these guys. Okay, so to answer your question.
Hello, sir.
I don't know. I'm not very sure to like how to relate to. I mean, your question is valid, but I don't know what to say because we just want to give some dimension to bounded geometrical objects. I would say that, okay, because yeah, and yeah, we just want to give some the concept of dimension to this. I would say that, yeah. Okay.
Hello, sir.
Yeah.
Hello, sir.
Yeah.
Sir, so simplex is nothing but convex combination of affinely independent vectors, right?
Yes, affine independent vectors, convex combination. So that's why you will get a boundary like this. Yeah. Yeah.
And also that V0 can be any one of the vector, or it's a specific vector in the set.
It is one of the vectors in the set. Any one of the vectors in the set. V0 is any one of the vector in the set.
Yeah. Okay.
Hello.
Hello. Yes.
Is there a relation between the cube and the tetrahedron, or is it just defining the k dimension?
Is there a
relation between the cube and the tetrahedron here, or is it just the representation of k axes?
Is there a relationship between Q and a tetrahedron?
Yes, sir. Or is it the axes?
Cube. She meant cube.
Cube, yeah. So cube. Is there any relation? No, this is just here to give you an idea of that. This is a three-dimensional object.
Okay.
This is just to give you a illusion of a 3D object. Yeah. It would be a good idea, actually. I'm thinking this time to create some assignments where actually you can plot these things and see what interesting simplexes you can generate. Okay, that would be an interesting exercise because you can generate a wide variety of things. Of course, visualization is a problem for us because we cannot do beyond 3D, right? Okay, so some of the common simplexes are, let us say 1D simplex will be a line, but line with like a boundary, right? So from here to here. Okay, because it will have a boundary, because that's how it is. It's a convex combinations. You will select 2 points, right? So V1 and V2, and then you will take a convex combination of that. So that will become a line. Okay, so that's a very simplest case. So that's how the convex combination we will do. There is a typo here, right? So it should be like this. It's determined by x1 and x2, which are endpoints of the line joining x1 and x2. Okay, 2D simplex is a triangle. Okay, so simplex can be generated by considering affinely independent points x1, x2, x3. Yes, so and then 3D simplex we just saw is a tetrahedron. Okay, so oh yeah, I think we made a mistake here, right? We have to start with 4 points, right? To get a tetrahedron, we have to start with the 4 points, right? Not the 3 points. So for a line we need 2 points. Okay, so for 1D, the way dimension was defined is for k dimensional, I need k plus 1 points, right? Okay, so for a line, I needed 2 points. For a triangle, I need 3 points. And for a tetrahedron, I need 4 points.
So we need 5 points, right?
Which one?
For tetrahedron. So
Yeah.
there'll be 5 and one of them will be V0. So we get 4 and then we join those 4 to get the tetrahedron.
No, I mean a tetrahedron, how does it look like, right?
I mean, affinely independent points 4, yes, but
yeah, something like this,
points,
right?
Yes, actual points
yeah.
will be 5.
So for the corner, yeah, we need corner points. It will be 4, right? Yeah, yeah, that's right. So it's fine, right? So triangle is like just this. So this is triangle. Okay, and tetrahedron we need 4. Okay, so there is no. Yeah. So and then this way we can. After this, like visualizing is a bit difficult, but yeah, we know what to do. Okay. Okay, so these are the examples of simplexes. There are special cases of simplexes. For instance, n-dimensional simplex. So this is a very special simplex. What is this? X greater than equal to 0 and 1 transpose X is less than equal to 1. So what this simplex means, like if we draw this, let us say in R2. So
it's a square.
So can you, yeah, can you visualize this? Like so what is this simplex? Is it like a square?
It's like a triangle.
It's like a triangle, right? So X greater than equal to 0, right? So X greater than equal to 0 and so let us say this is like E1, this is like E2, and then we have a 0 here. So let us consider this 0, E1, E2 case. And then sum of this must be less than equal to 1. So it must be bounded within this. Okay, so that will be the unit simplex, right? In R2, right? So if you do it, extend it, then in 3D, then it will look something like this. I don't know how to draw, and there will be a base point here. But bounded up to 1, right? So the sum of the components of your vector must be, and the reason why it is looking like a diamond shape is like a one norm ball, right? But the problem is like you are not allowing X greater than, so only this part will be left. So it's 3-dimensional. It's now very hard to visualize. So there is also a height here. Okay, something like this. So this is like a one norm, right? So this is one norm of X is less than equal to 1. So one norm of X is less than equal to 1. We know that it looked like a diamond shaped. Okay, and now we also have a restriction that X greater than equal to 0. So only this part will be remaining. Okay. Okay. So and then there is something called probability simplex. This may show up in some examples that require models of optimization problem with some probability involved. This is called robust programming or stochastic programming, and so those require they sometimes they have a noise in the data or so on. So then you have to use some probabilistic ideas and so on. So there is something called n-1 dimensional simplex determined by unit vectors e1 and en. So it's dot dot dot. It is the set of vectors that satisfy X greater than equal to 0 and 1 transpose X is equal to 1. Okay, the way it is defined is just equal here. Okay, that's probability, and the reason why it is equal to 1, it's like I can think of X as the possible probabilities that I'm going to have and we know that the sum of the probabilities must sum up to 1. Okay, so this is why this is a special case. We will see some examples of this. Okay, why these things are interesting.
So sir, it would be a line, no?
Yeah, x greater than equal to 0 and 1 transpose x is equal to 1. So what this will be? Actually, this will be a very special case because you will not include the inner parts, right? So it's like where one norm is equal to 1, right? So this is like a very special case. Yeah, so it will be like a line. Yeah, you're right. So it will be just this boundary part. Okay, these guys. X plus y is equal to 1 is this line, right? This is the x plus y equal to 1 line. And x and y both greater than equal to 0. Okay, so x comma y greater than equal to 0 because that is also a constraint here. Yeah. So or let's say x1, x2, these are x1 and x2 if you get confused. Okay, so that will be just a line. These things are useful in probabilistic models. We will see later on. Okay, we just keep this in mind. Okay, for the moment. Okay, there is an object which is called cone, and cone is different from norm cone. The definition is rather simple. A set C is called a cone if for every x in C, okay, so every x in the set C, theta and theta greater than equal to 0, we have theta x is also in C. Now, what type of figure it will become, right, with these constraints? So what is the constraint that we removed from the convex set? Only one constraint we removed. The first part we kept, and the other constraint was that the 1 transpose theta was 1. Okay, that is the sum of the components of theta must sum up to 1. That is something we removed in the case of cone. And if you do that, okay, from the convex case, if you drop just this part, that the sum of the theta must sum up to 1, then you get an object which is called cone. Okay. Now the question is whether cone will be convex. Okay, since you have dropped this, intuitively you can say that it may not be, and that is the case, right? So, okay, what can you see from the figure, right? Let us say I define the set. Let us say I give the set in which yeah, so let us say I give the set of all yeah, so from here itself, let me give you a set. Let us say my set contains alpha x1 union beta x1. Okay, so that will be line, right? So this is alpha x1 is this line. Okay, alpha x1, and this is the line beta x2, I mean. Okay, so you see in this case, the fact that you drop that sum of the theta must be 1. This means that there is no possibility of getting the inner points. Okay, you don't get these inner points now because so this is a cone. This is a valid cone. Okay, this is a cone. Because to check this is very simple for me because I take any point, so let y be in C. If y is in C, then y is either in here or either in here, right? So this implies y is, let us say without loss of generality, y is in alpha x1. Okay, so if y is in alpha x1, then y is of the form some beta x1. Okay, so y remain here only, right? So that means that y is in C because y is still again some scalar multiple. I mean, it is already there, right? So there's nothing to say. The way I define this example is a bit strange. But yeah, so what I'm trying to say is like just by taking this line and this line, it remains a cone. Okay, so that's a cone, but it is not convex because I take some point from here, some point from here, and I draw, and these points are now no longer guaranteed to be in the cone, right? So you can take some point a midpoint of x1 and x2, and that is not there in either of these. Okay, so a cone is not necessarily convex. Cone is not so, but is it always true that cone is not convex? I'm saying not necessarily. I'm not saying not always. So
No,
can
sir,
you
if
give
we
an example
include
of a
half
cone?
spaces,
Yes.
if we take half spaces in cone, then it would be convex.
Yes. So if you take half spaces, the half spaces are cone, but they are also convex. Okay. So let us say this half spaces. Okay. So you take this, then they form a cone. Okay, and they are also convex. Okay. Okay. But is line segment a cone? Like from here to here, it is convex, but is this a cone? Is line segment a cone?
If x1 and x2 are the same.
If x1 and x2 are the same.
Line segment need not be cones.
Yeah, need not be, right? Because there is arbitrary value of theta that, so if I'm somewhere here, if I take arbitrary value of theta, then theta times x, like x is here, will go way beyond the line. So that is no longer within the line. So hence it's not a cone. Okay. So there are quite a few examples. Yes.
We can consider a line.
We can consider a
Line instead of line segment.
Yeah. So if you consider a line segment, then both way it's valid. So it's convex as well as cone. Yeah, but if you but the otherwise is not true. Okay. So okay. Is it necessary that cone must have an origin? Is it
No,
necessary
sir.
that cone must have a origin point?
Not necessary, sir, because if we consider line, it doesn't have any origin.
Yes, so you think cone does not have origin, but see the definition.
Theta is 0, it will has to come.
Yeah, there is a theta 0, right? Allowed. So theta 0, so 0 times any vector, so it will be 0. So that 0 vector must be in the cone. Okay. So a cone must contain 0. By definition, cone must contain 0 always. Okay. So anyway, like you can, and then hence now we talk about convex cone. So cone which is also convex is called convex cone. Is very simple, right? In general, cone is not convex, but if it is cone, and so for instance here, if I also include the inner line in inner shaded area, then it becomes convex, and it remains a cone. So we can talk about something called a conic combination. Okay, so conic combination is a combination of this form where the theta is are greater than equal to 0, and the additional restriction that the sum of the theta is 1, that part is removed. So if you remove that condition from the convex combination definition, then what you get is a conic combination. Okay, so that's the conic. And then we can also form something called conic hull. Okay, so conic hull is like conic hull of a set is the set of all conic combinations of points in C. Okay, so it's any arbitrary C. Okay, this is any arbitrary C. I'm not saying that C is already a cone. You take any arbitrary C and you do a conic hull just like you did a convex hull. You make a conic hull and that will make it a cone. right? So initially I can start with any arbitrary points. Let us say any arbitrary points x1, x2, x3. OK, and then if I do a conic hull, then what will happen if because all will trace to origin, right? So origin is your reference point from where the cone will start, because origin is always there, right? So it must include, because theta is greater than or equal to 0, so it must include all these lines, right? So it must include this. OK, it must include this, and it must include this. OK, so that's the conic hull. Now the question is, what about like these points? Like, are there any other points also like generated in the conic hull? So what do you think? Like one thing is sure, like if I take x2, OK, and let us say x1, right? So if I take x1, if I just consider this term, then theta 1 x1 must be there. So that means that the line passing through x1 must be there. So whole line will be there. So that's done. If I take x2, then I just take the term theta 2 x2. Then the line passing through this, starting from origin, obviously, because theta is greater than or equal to 0. So then whole line will be there. Similarly, whole line will be there. But there are also addition terms, right? So what type of points they will generate? So like, can I say that any arbitrary point inside will also now be generated in the conic hull?
Could be, sir. That could be a possibility.
Yes, sir, because all of them will act as bases and they will cover the entire portion.
Yeah, so this is about vector space, like vector things that we recall, right? So like, what are the points? Let us say I see a point here, right? So I can generate these points, right? Because I can take some portion of this, and then I can take some portion of this, and then if I add, then I get this. So the way I will get is like, I will take this guy, the vector addition that we do, and put it here and scale it such that I get this. OK, that's how the vector addition works, right? So let me do this again, what I'm trying to say. OK, so we started with x1, we started with x2, we started with x3. OK, and any point, so I know for sure that the line passing through x1 will be there, x2 will be there, x3 will be there. But what I'm claiming is like any other point inside the boundary. So let us say our boundary was this, and our outermost boundary was, let us say this. OK, x2, let us say x2 is here. So what I'm claiming is that any other point here will also be generated, because it's very easy for me, because if I have to come here, I will see this, I will see this vector, and I will just do vector addition. So I will move it, translate it here. It will be bigger length, but I will take some possible theta, some theta prime of x2, so that it becomes contracted theta prime x2, and hence by vector addition I will get this. So this will be some theta 1 of x1, and this is theta prime of x2. I get this. So this way I can generate any point, even points inside. OK, I can generate, because then I can take a smaller contraction of this x1, so some theta, and then some theta times of this. I parallelly move this vector here, a vector addition, and then I move here. OK, so I can generate this way. I can generate any point inside. So convex hull will be a convex cone actually. OK, by definition. So that is something you can prove explicitly. OK, so I can put this in the assignment, that prove that the conic hull, and additionally you can prove that conic hull is the smallest convex cone containing C. OK, so you cannot get a or is it like I made a statement, it may be false, right? Like, is it like the smallest, like if I do a convex hull, is this the smallest cone let us say I do a convex hull of C. So convex hull of C. Okay. Convex hull of C. Is convex hull of C smallest cone containing C? Okay. So think about this. Is the convex hull of C smallest cone containing C? Convex hull is a cone, that's clear, right? I mean not convex hull, right? I mean conic hull, okay? So conic hull of C the smallest cone containing C? What do you think, right?
Yes, sir, because they will span the same area as C itself. If we consider C as basis vectors.
B as basis, like
Set C as basis vector will span the same area as the conic hull.
Yeah, but the question that I am asking is the following. Conic hull is a subset, okay, or the other way, right? Contains some let us say cone, okay, let us say C2, okay, and which contains C, but this is a proper, so this is like not equal. Okay, the question is this: does there exist a cone that contains the set C, but it is a proper subset of the conic hull?
So when you say small, like what do you mean by that? Like, how do we say small or smallest?
Yeah, by smallest I mean just extend C enough such that it becomes a cone. Remember, C in our case is just a set, not yet a cone. Now,
So we can.
how can I extend this such that it just becomes a cone, and there is nothing in below between this. It's the smallest cone that I get after extending this. I put entries in C such that I get the smallest cone. Okay, that's the question.
So
Okay,
we can prove by contradiction, taking one point is not present in the cone, which is present in the conic hull, and we can arrive at the contradiction that point must be present in the cone, so that the cone will be satisfying the property of.
But your answer is in which way? Like, what is the answer that you're going to?
I am assuming that the cone C has some points lesser than conic hull, but still it is satisfying all the properties of the cone, that it is convex and all. So we will take that single point that can be written as a linear combination as
No,
given.
but you did not answer my question. My question is very simple. Someone gives you a set C, okay? One possibility for you is that you can do a conic hull. You make a all possible conic combination, right?
Yes, sir.
And this becomes a cone for sure by definition. Now the question is, will there exist a set C2 properly lying between, it's a proper superset, let us say, of C and a proper subset of conic hull such that it is a cone? So what does you answer, yes or no? Like,
No,
will there
sir.
exist? No.
No.
Okay. So is this the same thing with other students? Like, can you tell me, like, that you also have same feeling, or if you differ, then you have to come up with some example, right?
How do we prove it's like we feel it's the smallest, but how do we prove it?
Yeah, so I mean, it's about, no, and it's not really about proving, right? It's about the about the definitions and the understanding you have. Let us say I start with some simple example. C is a set, not a cone yet. Okay, C is a set that contains some entries like this. Okay, and then definitely it's not a cone because theta x1 for different theta is not there. Only x1 is there, but let us say half of x1 is not there. Okay, so it's not a cone. Now I want to build a cone that is a containing C and is the smallest, right? So what should I do? What does cone definition ask you to do? Conical is fine. Like conical is somewhere here, right? So theta 1 x1 plus theta 2 x2 such that theta 1 and theta 2 are greater than equal to 0. Greater than equal to 0. That I know. So conical I can make. Okay, so this is the conical hull of C, right? That we get. Now, is there anything that I get somewhere here? Okay, subset. It's not a conic hull, but still a cone containing x1, x2.
And that cone will belong to the conic hull.
Which one?
The cone.
The cone.
Yeah, it belongs to the conic hull.
Yeah, exactly. If you make a cone of this, okay, if you make a cone of this, then it will be a it will not be a conic hull, but still be a cone. So what will be the cone that I'm looking for out of this?
Hello.
Yes.
All the cones with theta 1 plus theta 2 greater than 1.
Yeah, but x1 and x2 must be there, right? So what is this set I'm talking about? In terms of set, how should I write? To make this a cone, what should I do here? What you are saying is like in a right direction, but what should I write?
It's still theta 1 x1 plus theta 2 x2, but the constraint.
Why would you do plus? That's the main thing, right? If you do plus, then you get into hull, right? There is something in between. What I'm trying to say is there is something in between. Like I don't have to worry about intermediate points, right? I don't want to generate those, let us say, but I still want to make a cone, right?
So theta 1 x1 belongs to C, theta 2 x2 belongs to C. So I do not see.
Yeah, so write down union.
Yeah, union, yes.
X2, right? That's it. You see, this guy is a proper subset of this because it doesn't contain intermediate points, and this itself is a cone now because it's a union. So any y someone tells you it's either here or either here, and theta times that is there because all possible theta is already there in the set. So for any arbitrary y, theta y is there. So that's a cone. In other words, yeah. So what some of you said is like correct, right? So this is like x1 and this is like x2. That itself is a cone, and this was generated from x1, x2. But conic hull makes it convex in the sense like it also includes this part, right? Okay, so to answer my question, conic hull is not necessarily the smallest cone containing C. There could be a smaller cone containing C. Okay, but in the convex case, it's a bit different, right? In the convex case, so if you want to do a convex hull of this, okay, so you cannot have a convex set lying in between a convex hull and the set C. Okay, so this is what we discussed previously. So convex hull is the smallest convex set containing C. You cannot have anything in between. But in the conic hull, we saw that in conic hull there can be a cones that may lie in between the conic hull and the set C. In the convex case, it will never be the case. Okay, you cannot have a set which is convex and lying in between the set C and the convex hull. Okay, so that's so this type of true false questions might come in exams and so on. Okay, so this may not be in the slides. Actually, many things May not be in the slide, but you have to watch videos. If you are not watching video, you have. I mean, you are not. If you are not live, then you have to watch videos. Some of my questions are like this. Some of my questions are like I tell things orally. It may not be written down in the slides, but it may come in the exam. Okay. Okay. So this is the thing. Okay. So these are just definitions of how the conic hull looks like. So in this case, this is so important thing to note is the conic hulls do look like cone because you look for the boundary most point, and then you fill everything inside that. That's the conic hull. Even if you had just only 2 points, that is enough to fill everything. Like I said, like it is enough to fill everything. Okay. So
Hello,
I think we are already in time. Okay.
Hello,
Okay. You can ask question. Okay. Yes.
sir. So we can say conic hull of C is equal to convex hull of C.
Conic hull is also a convex hull, but it may but okay, that's a very good question.